let's have another application of second order differential equations. Let's now discuss series circuit analog. So for an LRC series circuit, we know that many different physical systems can be described by a linear second order differential equations similar to the differential equations of a force motion with damping. So m d squared x over dt plus beta dx over dt plus kx equal to f of t. Now, if I of t denote the current in an LRC series electric circuit shown in figure 5.1.17, then the voltage drop across the inductor, resistor, and capacitor. So we have this series circuits L, R, and C. So in an inductor, the voltage drop is equal to L di over dt. So it is the product of the inductance L and the change in current di over dt. The resistor from Ohm's law is current times resistance, so IR. While for the capacitor, it would be 1 over CQ. So we will be having a standard model of an LRC circuit. So applying Kirchhoff's second law, the sum of these voltages equal to the voltage E of t impressed on the circuit, that is L di over dt for the inductance, Ri for the resistance, and charge over C for the capacitance equal to the external voltage E of t. So, but the charge Q of t on the capacitor is related to the current I of t. So, I is the current, which is the change of the charge per unit time. So, this is the rate at which charge is flowing. So, dq over dt. So, this becomes a second order differential equations L d squared q over dt squared plus R dq over dt plus 1 over cq equal to E of t. So, the nomenclature used in the analysis of circuits is similar to that used to describe a spring mass system. If E of t is equal to 0, the electrical vibrations of the circuit are said to be free. So, if there's no impressed voltage. Because the auxiliary equation for 34 is Lm squared plus Rm plus 1 over C equal to 0. Therefore, there would be three forms of solution with R not equal to 0 depending on the value of the discriminant. So, we're going to consider yung R squared equal minus 4L over C. So, this would form the overdump, the critically damped, and the underdamped. Overdump, R squared minus 4L over C is greater than 0. Critically damped, R squared minus 4L over C equal to 0. So the roots would be equal. And underdamped, R squared minus 4L over C less than 0. So the roots would be complex conjugate. In each of these three cases, the general solution contains the factor e to the negative RT over 2L. Q of t approach 0 as t approach infinity. So it is a transient response because there is this e to the negative RT over 2L. So that would be the transient response. So in the underdamped case where Q of 0 is equal to Q sub 0, the charge of the capacitor oscillates as it decays. In other words, the capacitor is charging and discharging as t approach infinity. So it is charging, discharging, charging, discharging. When E of t is equal to 0 and R is equal to 0, the circuit is said to be undamped and the electrical vibrations do not approach 0 as t increases without bound. So the response of the circuit is a simple harmonic. We need this for communication systems. So for example, find the charge Q of t on the capacitor in an LRC series circuit when L is equal to 0.25 henries, R is equal to 10 ohms, C is equal to 0.001 farad, E of t is equal to 0, Q of 0 is equal to Q sub 0 columns, and I of 0 is equal to 0. So we're going to plug in everything to the model. That would be L d squared q over dt plus r dq over dt plus 1 over cq equal to E. So L is 0.25, which is 1/4. R is 10. And 1 over C, so 1 over 0.001, so that's 1000 Q equal to 0. We multiply everything by 4. So Q double prime plus 40Q prime plus 4000 Q is equal to 0. Solving for this homogeneous equation, the usual manner, we find that the circuit is underdamped. So we have m squared plus 40m equal to negative 4,000. So 20 squared. So plus 20 squared. So it would be negative 20 plus or minus. So this is negative 3,600. So that's 60. So we have e to the negative 20t, C1 cosine 60t plus C2 sine 60t. Applying the initial condition that C1 is equal to Q sub 0 and applying the initial conditions, we have Q sub 0 is equal to 0 and Q prime, which is the current, is equal to 0. So we're going to have C1 is equal to Q sub 0 and C2 is equal to 1/3 Q sub 0. So thus, the resulting function is Q of t is equal to Q sub 0 e to the negative 20t times cosine 60t plus 1/3 60t. Using this, we can write the foregoing solution as Q of t is equal to Q sub 0 square root of 10 over 3. So we just solve for the square root of C1 squared plus C2 squared. So that would be 1 squared is 1 plus 1/3 squared is 1 over 9. So square root of 1 plus 1 over 9 is square root of 10 over 9. So that's 10 over 3, square root of 10 over 3, Q sub 0. And then we get phi to be inverse tangent of C1 over C2. So that would be 1.249. So when there is an impressed voltage E of t on the circuit, the electrical vibrations are said to be forced. In the case when R is not equal to 0, the complementary function is called a transient solution. If E of t is a periodic or a constant, then the particular solution Q of t is a steady state solution. So for example, find the steady state solution QP of t and the steady state current in an LRC series circuit when the impressed voltage is E sub 0 sine gamma t. So the steady state solution Q of P is a particular solution to the differential equation Q double prime plus RQ prime plus 1 over CQ is equal to E sine gamma t. Using the method of undetermined coefficients, we assume that the particular solution is A sine gamma t plus B cosine gamma t. Substituting this expression into the differential equations, simplifying and equating coefficients, this gives A to be equal to E sub 0 L gamma minus 1 over C gamma all over negative gamma times L squared gamma squared minus 2L over C plus 1 over C squared gamma squared plus R squared, while B is E sub 0 R over negative gamma times L squared gamma squared minus 2L over C plus 1 over C squared gamma squared plus R squared. It is convenient to express A and B in terms of some new symbols. So X is L gamma minus 1 over C gamma, and X squared is L squared gamma squared minus 2L over C plus 1 over C squared gamma squared. And thus, Z is equal to square root of X squared plus R squared, which is then Z squared equal to L squared gamma squared minus 2L over C plus 1 over C squared gamma squared plus R squared. So if you want to get the solution to a network problem for LRC circuit, you can use this set of formulas. So we can have A to be equal to EX over negative gamma Z squared and B equal to E sub 0 R over negative gamma Z squared. So A is the reactance and B is the resistance. So the steady state charge is given by Q of P is equal to negative E sub O x over negative gamma Z squared sine gamma T minus E sub 0 R over negative gamma Z squared cosine gamma T. So now the steady state current is given by IP equal to Q prime. So we differentiate this to get the current. So the charge is Q. So the current is dQ over dt. So we differentiate charge with respect to time. So IP is equal to E sub 0 over Z R over Z sine gamma t minus X over Z cosine gamma t. So the quantities X equal to L gamma minus 1 over C gamma and Z equal to square root of X squared plus R squared defined in example 10 are called the reactances and impedances respectively of the circuit. So R is resistance, X is reactance, Z is the impedance. Both the reactance and the impedance are measured similar to resistance in ohms.